This video is a short getting started video demonstrating how to build extensible blockchain object model XBOM classes. This is not a source video, it is demonstrating just the build path, what it takes to compile the code and have it ready to be dynamically loaded by the class manager infrastructure. Other videos in source themselves are available online about how to build the specific classes. As shown in a previous video, the installation script, which can be downloaded using a curl command from the GitLab sources, creates in the directory home Prasaga, which you have to put in that directory, the fabric samples and the XBOM sources for the public community sources. What we're going to do is do a build of the classes individually rather than the full setup, and then explain how the rest of it happens. This is the classes directory. And you'll see that there's the individual classes. If we go to any one of them, like count, you can see that there is a skeleton, a stub, an implementation, and then other stubs that are used by the class. These are all in the same directory. These other stubs are usually linked to it with Linux soft links, as can be shown here. And you can see that also in other directories. Let's look at class factory. You see the same thing. Here's the class factory implementation file. Here's the class factory skeleton. Here's the class factory stub. Here's the other soft links. And I've skipped what the .so is. The .so file is the actual Go plugin that's built. We're going to go do that in a minute. I'm going to copy it over. All Go plugins, we use the Go language for the class manager infrastructure and for all the classes, are in fact regular Linux shared objects, and they are loaded dynamically by the system at the base of it using the equivalent of the ld.so to dynamically link. The class manager infrastructure does this explicitly using the Go runtime environment. Let's go actually take a look at how they're built. So there's a simple script, build script, that you can find in the build directory. Obviously, you're free to modify these things any way you feel like. This is just as an example. A couple of key things. The first one is that the Go path, this variable right here, must be set. And this is an environment variable used by the Go runtime environment. I'm sorry, the Go build environment, the Go compiler. It's very important because this gives the path to where the import packages are that are used as the interface to the class manager infrastructure runtime. And there's two packages that are pathed to, and you can see it in all the sources, three of them actually, and I'll actually show that out. I'll show what the import command is in one of the sources in a second after we do a build. And they are object encode decode, class manager types, which is the interface to the class manager infrastructure, and something we call forced cast, which was just a tool to make it easier to do typecasting with the Go language environment. The XBOM core path must be set to /home/prasaga/XBOM. The XBOM classes right now happens to be set to the same path as well, and we do that just because that's where we happen to put the classes, but you could have your classes built anywhere you want. It's the fact that you have the Go path correct that's important. Okay, the command to actually do the build is this right here, go build. dash build mode equals plugin. You have to have that switch, otherwise we'll try to build binary, try to build a final executable, not a shared object. And you build that in the directory with those source files, and it will just build them all together. That's really nice. You don't need to explicitly list the files. You don't need to do anything. Puts them all together, names the shared object by the name of the directory as the output, and then we copy that into this directory, the build directory, and we rename it to what we want the class name to actually be. And this is the name that's actually used at runtime. It's what's given to the Go runtime environment by the class infrastructure through the class file loader class to load a new class. To see it running, very simple. We use bash with the -x to show us the commands. And here you can see that it set the go path. Here's the go path right here being set. Okay. Here's the go build command. There's no errors, just finishes. Here's the copy command to copy it into the new name. Does for all of these, and if I do an ls, here's all the new classes. And by the way, to prove that they were just made, they were made, excuse me, they were all made just now, and it is in fact September 30th at 18:17 now. So that's how the classes are built. Okay. One thing before we go into how we put them right now into the test environment, which is strictly how the test network environment works. You don't have to use. It's not required. It's how we create a development environment. Let's go look at the source just real quickly about what a source looks like for importing. So let's look at a implementation file. Sorry. You'll notice at the top the import command. This is a Go type command. And these are the three packages that are specific to class manager infrastructure. Object, inc, dec for object encode decode, class manager types. This is the actual interface file. And this one file, forced cast, which is how we do the command cast, which you can see used. It's literally a typecast. You can see used farther down. So here's an example of using cast, and it's just a way to avoid some ugly syntax. It's not required, just makes things a lot easier, and we recommend everybody use it. At the top of the file, let me get to the top of the file. Run that again. You'll notice that the package name is main. So this is important. All class plugins, all Go plugins, always are of type package main. So the package system built into the Go environment, as far as plugins are concerned, cannot really be used. This has to do with limitations with the pathing for the package names. It uses the actual directory path names. There may be a way to override it. Have not put the effort into figuring out how that's overridden. Looking through online environments, basically it looks like the intent was originally to build everything from sources, and with the XBOM environment, we are loading binary at runtime with the Hyperledger Fabric blockchain. We're not trying to build all these sources out at that time. There's a lot of reasons for that. One of the ones is, of course, that because we dynamically load the classes onto all the nodes in a blockchain as needed, we wouldn't want every one of them to try to compile it independently. Not only that, they'd have to have the compiler environment. Okay, now that we've seen how it's built, now the next question to address is how does it actually get loaded into the test environment? So when we go over to the test environment, which is in samples, first let's go look at test network. And I happen to want to go into the Docker directory because of the explicit change in the test network system. So the test network creates one orderer in two peers. They're right here. That happens to be the names of the volumes for, but same thing. We didn't touch the orderer. It works as is. However, Down here, you'll notice the production directory, which is used for the external build. And I'll explain that in a second. And you can look that up in how to do an external build in the Hyperledger Fabric tutorials. And we path to the scripts right here. And I'll show you what those scripts are. Those are for the external build environment. And here we would bring in the classes. And then we set up the working dir, and this was a default behavior you'll find in the environment already. Okay. So this Docker compose file is slightly different than the default for test network. That's what I'm pointing out. And what we want to do is now look into where the chain code is. So in the chain code, we've added our chain code because the class manager infrastructure is loaded as though it's chain code, even though it's a class manager infrastructure. And it's interfaced that way as well. However, to do an external build, there's two things that are necessary. And sorry, not external build, an external chain code. There's a couple pieces that are involved, and reading through the Hyperledger Fabric tutorial will help quite a bit. However, the pieces that we put together, you can see in the make tgz, which means make tar gzip is what we named it that. It's actually this file that has the chain code in it. Take a quick look at the script itself. As can be seen, it's doing the actual setting up the path. It's going and doing an initial build into the, as though they were building the core system. This is a no-op, it's already done. Here's the one that is actually building the classes and runs the script that I just showed you right here. Then more importantly, down here, we copy all the binaries, all the executable and shared object plugins into a single source directory. Could be, and then we tar it into, it's called code.tar.gzip. Now the reason why you do this is because the external build environment for chain code for Hyperledger v2.0 and beyond will take this and send it to the individual nodes when you're doing a chain code install and put it into the production directory. And we're running in a container environment, so it's putting in a virtual directory tree because we put that into Docker Compose. And then notice that it's tarring up not only the main binary, but all the classes as well. So it puts them out everywhere. This is a test environment. In a real environment, we would also want to be able to pull classes down, class implementation files from URLs from anywhere that we've set up, or even off of a local directory. For a development environment, we just stuck it all in the same file. And then the next tar is the piece that you're actually going to load, and you need to put in the source file, and it's called the metadata.json. And let's just take a look at the metadata.json. You'll notice that it simply names the file, and this is just a requirement to make the system run. Again, you can read the tutorial for this. The other piece missing, though, is the scripts that actually build this. And as you notice, I pointed out that it loads the class manager scripts, and here they are. Build, detect, run. So the detect, remember this is a development environment, so we did as minimal as possible. So the detect environment, here I'll clear the screen and do that again. Basically does nothing. It says as long as I'm actually loading, I have the metadata.json file and that I can find Golang in it, then I'm good. Basically, this is mostly default, slightly edited, but most of it you can find by the standard setup. Then it'll do the build and the run. And there's one more if you want to read the documentation, but we don't use it in this environment. 4 files, 4 scripts. And this one does, it fakes out, normally you would do an extract and an actual build. We don't actually do that. All we do is we simply copy to the passed in output directory right here, and here we copy in the chain code because the name it needs to be called is chain code. Then finally the run. Sets up the environment as you would find with, again, this is all standard, as you'd find with any of the environment. I do echo this so it shows up in the log file, but you can do what you want. And then simply does call here, exec the chain code, replace script of the chain code process, which is just standard behavior. And here it's running the chain class manager, and it's passing in the peer address. And this path is, we use that to actually find the classes that, of course, I showed previously are actually distributed with the chain code class manager infrastructure for the test environment. But again, that could be, we could just easily, when we're using a class file loader, to be passing it, having it, loading it off of a URL or something like that. Again, this is a test environment. Actually, just one quickie, we'll run back through the chain code. Actually run it once, just that script. I'll remove the class manager.tgz, and we'll remove the code.tar, and we'll simply do a and it's just going to run through. Here's where it's doing the tar that I was showing you. It's bringing in the pre-built that are the class manager infrastructure right here. Actually did the copies here. It does the tar here of the code.tar.gz. And then here's the command to actually put together the class manager.tgz, and it adds in metadata in the code.tar.gz. After that, the rest of it, you've previous video shows how the peers are launched and run. In another video, we can take a walk through some of the class manager, not class manager, the classes sources. There's the 3 critical files, the stub files, the skeleton file, and the implementation file, and discuss some of the anatomy for that in more detail than some of the earlier videos. By the way, just to kick this off, I'm not going to let it run, but I will demonstrate the test network running. Let me pull up a script and just show that it starts up and runs. That's literally what we did before, same as the previous video. File. And do a paste. Oh, sorry. And it's important that you actually have a Docker daemon running. Try again. There you go, now Docker's running. And let's try that script again. And we're up and running. There's the images running. I'm not going to let it run all the way through, but basically it starts up, the Docker Composer runs. As you can see, those are up and running, and the system's running. Thank you very much. That's it for this video. This a quick walkthrough of how to build and install XBOM classes into the environment for the test network. For more information about Prasaga and the extensible blockchain object model, visit prasaga.com, and there's email and Telegram channels and things like that to reach out to us. Thank you very much.